In this video, we're going to talk about acid dissociation constants. They're basically the main way we determine whether an acid is strong or weak. So, here we go. The main way to quantitatively measure an acid's strength is by determining or using its acid dissociation constant. We know that strong acids are when they ionize completely, but we often don't know that just by looking at a compound. The Ka of that compound is what really gives us an idea how much it dissociates. Basically, the higher the Ka, the stronger the acid. Actual, quote, strong acids, we've only got about 7 of those. Typically, their K values will be greater than 1. Basically, anything less than 1 typically will be a weak acid. Sometimes actually turns into a base if it gets really low enough. Again, keep in mind that the more positive the number, the bigger it is. But, yeah. The Ka of an acid is the ratio of the concentration of the dissociated form of an acid to the concentration of the undissociated form. It basically measures or gives you an actual reference point of how much of this acid will actually dissociate. The higher the Ka then, the more it will dissociate, which is why we say the stronger the acid. The lower it gets, the more undissociated it will stay. In other words, it is the ratio of what we end up with at equilibrium over what we started with. So it's dissociated over undissociated, or what we end with over what we start. The larger this number, and actually this is very similar to what we originally defined things as products over reactants. The larger the Ka, the more we'll end with compared to what we start with. The smaller it is, the more we're gonna, the less we're gonna really have at the end, and the more we're gonna end up with basically in our original form. This is like saying when HF dissociates into H plus and F minus, the larger the Ka, more so if we look at a solution of hydrofluoric acid, we're probably going to see some HF just broke together. We're going to also see some H and some F. So we're going to see both sides of this equation. The larger the Ka, the more of this we're going to see. And the smaller the Ka, the more of this we're going to see. You'll still see all three, if you will, or both sides. But the larger the Ka, the more of the products you're going to see. With strong acids, by the way, you won't see any of the original. You'll just see what they dissociate into, which is why we call them strong acids. To determine the Ka of a weak acid, we typically have to use an ice table. Mainly because we're not exactly sure how much of it will remain at equilibrium. We'll be given some values, but to actually determine the Ka, we have to do a little bit of math to use those values to determine what our numbers tell us about our acid. An ice table basically stands, the ice, as you probably figured, stands for 3 different things. So to make an ice table, follow these steps. First off, you're going to write the balanced equation for the reaction. I'm going to go back to that hydrofluoric example and rewrite our balanced equation. Most of the time, there aren't really any coefficients when dealing with Ka. If you're interested in AP chemistry, I'll give you a couple in AP Chem, but even at higher levels, you normally just don't have a whole lot because you're dealing with one compound and most acids are what we call monoprotic, meaning they only have one H that they'll be donating, not 2 or 3, which means you end up balancing everything with coefficients of 1. You can assume, by the way, that unless otherwise told, I'm actually going to mention this later, all your acids are monoproduct, meaning they're balanced without really having to do anything. Number 2, you write any initial concentrations you are given. And for products, this will typically be 0. So again, we have that balanced equation. An ice table, the very first row, stands for initial. This is where you write any initial concentrations you're given. Products, this will typically be 0. And often they'll give you some concentration to start with. They'll say, we had 0.1 molar concentration of this acid. They'll give you that information. So we put that here. And that is our first row, initial. Our second row stands for change. This will represent the change that occurs in the chemicals involved in the reaction. Reactants will always have a negative change. Products will always have a positive change because the reactants will be decreasing to make the products, which means the products will increase. Stoichiometrically, every compound should experience the same change. So if our initial is back at the previous one, typically we won't know our change, so we put an X. However, whatever numbers here should all be the same according to the coefficients. For example, if somehow I balanced and got a 2 up here, this should be a 2x. Or if this is a 3, 3x. Okay? Or, actually, one last case. If this was a 2 and we defined that as x, then these should be half x. Because we're defining x as something that required 2. It comes down to stoichiometry. Most of the time, like I said, your coefficients are going to just be 1, so you won't have to worry about this much. But nonetheless, make sure that they're the same, and especially make sure that reactants are negative, products are positive. Lastly, you have the equilibrium row. So we have HF, and back with the original problem. Again, I just gave you the 0.1. You wouldn't have known that without being told. Your equilibrium, or the initial values minus your change values, equals your equilibrium values. Because basically we say, if this is the change that we went through without the reaction, here's our ending result. So this means this will be 0.1 minus x. This will be x, and this will be x. These values are then plugged into an equation for Ka in order to determine our Ka. So, as a reminder, our Ka is based the same way as equilibrium constants would. So for this case, it would be H plus times F minus over HF, which is products over reactants. So if using this equation, these values are what get plugged into our equation. So this will turn into x times x over 0.1 minus x. And that all will equal our Ka. This allows us to solve for x. Normally we'll end up solving for Ka. It'll actually give us enough information to determine our x. But that's really about all we do so far. So again, initial, what we change by, what we end up with, and we can plug what we end up with into our Ka. As I mentioned before, most acids are monoproduct, meaning they'll only dissociate one hydrogen. This makes our life a lot easier in that we really don't have to do much balancing for our ice tables. That means that we typically assume that all coefficients will be a 1, unless you're told otherwise. Occasionally you'll see what's called a base dissociation constant. It's calculated the exact same way as our Ka, just deals with acids. So the higher the Kb, the stronger the base, which is the exact opposite. So the higher the Ka, the stronger the acid, but also the weaker the base. And the stronger the Kb, the higher, the stronger the base, that also means it's a weaker acid. And typically it's dealing with hydroxide instead of hydrogen. So let's practice. In a 0.10 molar solution of methanoic acid, our hydrogen concentration is that. Calculate the Ka of this acid. I'm going to actually walk you through this one, let you try the second. Pretty much any time you're being asked to calculate Ka, you need to use an ice table. So I'm going to make one real quick. Oh, and methanoic acid I forgot to give to you, so give me just a second. Okay, so I'll talk for a bit, and I may end up pausing to let you write. Methanoic acid is this. It produces hydrogen and our leftover anion. Most, by the way, weak acids you're dealing with are going to follow this pattern, and that you've got an acid producing H plus and something else. So even if you don't really know the compound, you can basically assume there's probably going to be 3 columns. 2 of them will be products. One of those products will be hydrogen, and that'll be good enough for you. I'm just putting that squiggly line to differentiate between reactants and products. You also do not have to be this detailed in actually drawing all the lines of the table. I just kind of wanted to this time. So, balance equation, initial, change, and equilibrium. I'm going to pause for a bit, and I want you to try and fill out as much as you can. Now, that may not be a whole lot, but I at least want you to try it. Just give you about a minute or so. Okay. So, hopefully you got something written down. If not, that's okay. Just make sure you're paying attention. We are starting with a 0.1 molar solution of this acid. That means our initial is 0.1000 molar. We're just starting with the acid, which means we're not starting with any hydrogen, and we're not starting with any anion. Methanoate, I believe is what it's called. Okay? We're not really sure how much things are changing by. So, classic minus x, and plus x. Now, you may not have quite understood this, but this is saying that in this acid, when it hits equilibrium, this is our hydrogen concentration. Which means that goes right down here. And we're not really sure how much anion we have. We're not really sure, I'm going to shorten this to 0.1, how much acid we lost. Alright, now here's my opinion where it starts getting fun. Because you're looking at this and you're like, I don't know what in the world I'm doing. And don't worry, that's kind of how AP feels when they look at these. That's how everyone feels when they look at these. Here's where the reason I like it is because they're not that bad. Especially at how much you're going to be doing. So, let's pretend, well, more so, our Ka, if we were to calculate it out, technically would be 4.2 times 10 to the negative 3 times x over 0.1 minus x. But we don't know what our K is, and we don't know what x is, which means we really can't do anything with this. Except, my hope is that, actually, let me go and pause the video. Talk amongst yourselves or the class, what ideas do you have? There's something we can definitely do. My hope is you've seen it, but you may not have. So pause a bit, think, and come on back. Okay, hopefully you've noticed that we somehow added 0 and x and got x, and we added 0 and x and got 4.2. What that means is that this plus this equals this. Well, 0 plus x is just x, which means x is equal to 4.2 times 10 to the negative third, which makes our life quite a bit easier. Because that means, again, sorry, let me actually write this somewhere. 0 plus x is equal to 4.2 times 10 to the negative third. And again, we got that number because they told us that's our hydrogen concentration. Sometimes they're actually going to give you the pH of this, but you know how to go from pH to H. It's just 10 to the negative pH. Not too bad. Anyways, though, that means that x is equal to 4.2 times 10 to the negative 3. That means that our Ka actually now turns into, well, actually I'm kind of running out of rooms. I'm going to rewrite this. Hopefully you've got this written down somewhere. So this turns into 4.2 times 10 to the negative 3 times 4.2 times 10 to the negative 3 over 0.1 minus 4.2 times 10 to the negative 3. Okay, to make your life a lot easier, let's calculate the top, and then let's calculate the bottom, as we kind of used to, and then multiply top and bottom. So, let me kind of draw this arrow to show you where I'll be putting my answers. That turns into, so our top is equal to 1.76 times 10 to the negative 5 over 9.6, actually 5.8 times 10 to the negative 2. When you multiply that together, well, divide that together, you get 1.84 times 10 to the negative 4th. And that is our Ka. Now I know that's a lot of work, but you'll find that's basically the same process you do almost every single problem I give you. And you quickly get to the point where you're like, oh, I just kind of plug in numbers. So, hopefully that helped. Here's another example. Alright, in this example, I don't tell you what acid, but again, you really don't care. What you can do is actually set up your equation like this. It's a very common way. Where A minus base represents the leftover acid, and HA represents the leftover acid with the H with it. So then you're good from there. Have fun, good luck, come back in a few minutes. Okay, here's our ice table. Again, we're in the very same situation, and that X apparently is equal to this 9.86. That means our Ka can be written as this, which if we plug in our value of X, we get 9.86 times 10 to the negative 4. We have two of them on top, so I just tend to square them over 0.2 minus that number. Multiplying top and bottom now, we get 9.72 times 10 to the negative 7th over 0.199. And our final answer is 4.88 times 10 to the negative 6. So, ice tables can look hard, but overall, they're not too bad. There's just a lot of stuff written places. You'll find, though, it's basically the same type of pattern. That's ice tables. Thanks for watching.